Alright, hi everyone. Here's the video on heating curves, vapor pressure, boiling point, and phase diagrams. We'll start with section 1, heating curves. Feel free to skip around in this video. If you feel like you have heating curves down, go ahead and fast forward until we get to the section that you want to work on. Okay, so for heating curves, question number 1 says, in the diagrams above, label where substance A and B is a solid, a liquid, and a gas. Okay, so in the heating curve, remember what we're doing. Let's look at, this is a heating curve because the temperature is going up. This is a cooling curve because the temperature is going down. Let's look at the heating curve first. Basically, it's showing us as we add heat to something, what its temperature does. And when we started this, before we started this unit, you might have thought, oh, as I heat something, the temperature just goes steadily up. But that's actually not what happens because it takes energy for that substance to go through a phase change. And so while it's going through a phase change, all of the heat that's going into it is devoted into changing phase and not raising the temperature. So the temperature only raises when it's not going through a phase change. All right, so if substance B here, we've got low temperatures, this is one phase, this is another phase, this is another phase, because temperature is only going up when it's a single phase. I know that my coldest one must be solid, my next warmest must be liquid, and my hottest must be gas. So then these phase changes here, going from solid to liquid, that's going to be melting. And when something is melting, I can have both solid and liquid phases present at that same melting temperature. Same from liquid to gas, I can have liquid and gas as vaporization is occurring. Now, cooling curve is the exact same thing, but it's cooling down. So this hottest, so we still have the phase can only be, or the temperature can only be changing when we have one phase. When we are going through a phase change, all of that energy being taken out is being taken out through the phase change and not changing temperature. So these are phase changes. These are just single phases. All right, so my hottest phase is going to be gas, and then liquid, and then solid. Here I've got a phase change, so I have gas and liquid. So this would be condensation right there, gas becoming a liquid. And then I have liquid and solid, that would be freezing. Now it tells me to go ahead and label those things where they belong. So freezing, I said this as I was going, something is cooling, it's going from liquid to solid, so this would be freezing. And then melting is going to be from solid to liquid. Vaporization is going from liquid to gas, so here is vaporization. And then condensation is going from gas to liquid, so here is condensation. Okay, and one important thing to know is that the cooling curve, these temperatures where my phase changes occur would be the exact same if I had a heating curve. This would be the melting temperature, and this would be the vaporization temperature. So that will be important to know as you do the guided practice questions. All right, let's look at some vapor pressure. So first let's talk about what vapor pressure is again. It's been a while. So if you look at this container of liquid here, whenever you have liquid, and it doesn't have to be in a closed container, just whenever you have a liquid, some of the particles at the surface of the liquid have enough energy to escape and become gas particles. Okay, so some of these evaporate, and now we have gas above our liquid. We always have gas above our liquid. Now, whenever we have a gas, we know that those particles are going to be moving around and bouncing off the walls of the container. Okay, so sorry, I should have labeled this. These particles are our vapor particles. Okay, and then when they bounce off the container walls, okay, they create vapor pressure. Okay, so vapor pressure is just the pressure created by a liquid's evaporated particles. All right, so keep that in mind. A liquid, oh, sorry, and actually, before we go here, I just want to draw your attention to these vapor pressure curves. This is showing how the vapor pressure changes as we heat something. Okay, and so if you look at water, for example, that's this line. As we heat water up, notice that the pressure of its vapor is going up and up and up too. Because as we heat that water, the vapor we get more vapor because more particles can escape, and those particles are moving faster. And so we've got more particles hitting the sides of the container, and they're moving faster, and so they're hitting the sides of the container harder, and that's why vapor pressure goes up as we heat the liquid water, or any liquid for that matter. Okay, so when we heat water to a certain point, we know that it's going to boil. A liquid boils when its vapor pressure equals atmospheric pressure. Okay, and then the normal boiling point of the liquid is the temperature when its vapor pressure reaches 1 atmosphere, because that's the atmospheric pressure normally at sea level. So the normal boiling point is the temperature when the vapor pressure gets to 1 atmosphere, and we call that normal boiling point. Okay, so let's use these graphs and answer these questions. Question 1, what is the vapor pressure of water at 40 degrees Celsius? Okay, so at 40 degrees Celsius, here's my water line. So the vapor pressure is going to be like right here-ish. That looks like about 1/3 of the way up, so that's going to be 50 millimeters mercury is my unit of pressure. What's the normal boiling point of ether? Okay, so ether and the normal boiling point. So when does its vapor pressure reach 1 atm? Well, these units are not atm, they're millimeters mercury. But I know from this set of equivalent pressures that 760 millimeters mercury equals 1 atm. So I'm looking for the temperature when ether's vapor pressure gets up to 760, which is pretty close. It looks like a double line right there. So ether gets up to 760 at about 35 degrees Celsius. So that's the normal boiling point of ether. That's the temperature it would boil at sea level. Okay, number 3, if you go below the ocean floor to a place where the pressure is 900 millimeters mercury, at what temperature would benzene boil? Okay, so it's not going to be the normal boiling point anymore because the atmospheric pressure is not 1 atmosphere. It's more than that. It's 900 millimeters mercury. So we want to know how we'd have to get it hotter to get the vapor pressure that much higher. So let's look at benzene and see when its vapor pressure gets up to, here's 900. Okay, so there's benzene getting up to 900. That looks like it happens at about 85 degrees Celsius. Okay. Go ahead and do the guided practice for that section, and we will move on to section 3. Okay, so section 3, phase diagrams. So in phase diagrams, we basically have a temperature versus pressure graph, and it shows us what state the substance would be in at every different set of conditions of temperature versus pressure. And they're divided into regions, and then they're labeled. So anything in this region, any point that lands in this region means that at those conditions, the substance is a vapor. Any point that lands in this region means that at those conditions, the substance is a liquid. And if your conditions land in this region, that means that the substance is a solid. Okay, so let's go ahead and look through these questions. Question 1, what state of matter will water be in at 95 degrees Celsius and 0.0060 atm? So all we need to do is plot those conditions and see which region it falls in. Okay, so 95 degrees Celsius is going to be about here. 0.0060 atm is right about there. Okay, so that is in the vapor region. So that means that this substance, water, will be a vapor at those conditions. Okay, number 2, name the phase change or changes that occur at 1 atmosphere and 0 degrees Celsius. Okay, let's find that point, 1 atmosphere and 0 degrees Celsius. Okay, so that point falls on a phase boundary, which means that it falls on the line between 2 different regions. So if a point is on the line, it means that at those conditions, it could belong to either region. It could be solid or liquid. And so if it can be solid or liquid, this also means at this boundary, a phase change can be occurring. And so it would be the phase change between solid and liquid or liquid and solid. Those are called freezing and melting. So both of those could be occurring at that given set of conditions. Question 3. What states of matter will water be in at a temperature of 100 degrees Celsius and a pressure of 1 atmosphere? Okay, 100 degrees Celsius, 1 atmosphere right there. Again, this is on a phase boundary, so that means water could be in a state of liquid or a state of vapor. And the question doesn't ask what phase changes could be occurring, but phase changes can happen at any point on the line because you can have both phases present. And so we could have the phase change from liquid to vapor, which would be vaporization, or vapor to liquid, which would be condensation. Okay, number 4. What phases are present at 0.006 atmospheres and 0.01 degrees Celsius? So 0.006 atmospheres and 0.01 degrees Celsius. That's the triple point. So that's the point where all 3 regions intersect. And so we can have all 3 phases at that one set of conditions. So solid, liquid, and vapor. Okay, and then number 5. What is the minimum pressure required for liquid water to be present? Okay, so if we look at the liquid region, these are all the conditions where we can have liquid water. Okay, but it's saying what's the minimum pressure required. So if I were to take a sticky note and make a line out of that sticky note, like right here, for example. At this pressure, whatever that pressure is, notice that no matter how I change my temperature, I'm going to make this a dotted line so you can still see the graph. No matter how I change my temperature, so if I have a really low temperature, I could have a solid, but if I have a higher temperature, I'd have a vapor. No matter what the temperature is, I can't have a liquid. Whereas if I go up here to this pressure, so a little bit higher than 1, I could have a solid if my temperature is low, I could have a liquid if my temperature is medium, I could have a vapor if my temperature is higher. So where is it, where's that boundary where I first start being able to have liquid? Well, and now you can see it's when that line gets raised up right to the corner of the liquid region. And so that looks like about 0.0060 atmospheres. If I'm at that pressure, then I can have liquid right there at that temperature. Okay, so the minimum pressure required for liquid to be present would be 0.0060 atmospheres.